I guess we are all ready to go. Just a quick intro, because we don't have a lot of time. We have the center, which is called Innovation Center of Kosovo. We have the Washington Education in Kosovo, another center here that we have joined. And then we have the Washington Education in Albania, joining from Tirana, Albania, another country. Victor, I already put for an introduction. I talked about you briefly before you joined, so I'll let you move forward and start your presentation. It's very exciting to be here, and I know all of these guys here are so hungry to hear what you got to say.
Okay, so good. Thank you everyone for joining this session. Should I start sharing my slides, or let's see?
Sure. Yeah, on the left side there is a green button.
Okay, so let's see.
You move your mouse over, there is like a slide.
Okay, probably do this.
Here we go. We can see your screen now.
Can you see the slides?
Yes.
Okay, good. So good morning, everyone. Thanks, good evening, everyone. Thanks for joining me to talk about processor history and future. Well, I guess Ruben talked a little bit about me, so just quickly wrap up this part. So I've been working on processor design for about 20 years now. So I worked on many of the Intel processor. You know, some of these are really old, like Pentium Pros, probably almost like 20 years ago. All the way up to the latest one is the Xeon 5, which is a coprocessor that goes into supercomputers. And in terms of my interest is really how do we build efficient processor architecture as well as efficient programming environment. So we'll hear more about it today, and hopefully you'll learn something. First, I guess I want to kind of introduce, I'm sure everybody knows what a processor is. It's essentially the brain of a computer. Now, it does more than just word processing, spreadsheet calculation. It lets you, today's computer lets you browse the internet, allows you to play games. It will also even recognize your voice command, finding pictures in the archive. To some more exotic, more in the business world, it's actually helped the company analyze what the customer buying behavior is like, so that they can actually put more advertisement in front of you or put new products in front of you so that they entice you to buy. From the science world, it helps you discover new things. And then obviously from the government's point of view is how them track the terrorists and preventing them for creating great damage to the country. Now, what is a program? Now, we talked about a computer, a processor. A processor literally, just at this point doesn't really think on its own. It's like a brain, but it's not like our human brain that we can think. So a processor needs to be told what to do. And the things that tells it what to do is it's what we call a program. And here it's some, I just put in some C codes here, but of course, right, today's processor, today's programs are actually written in many, many different languages, C, Java, some of the scripting languages, etc. But the thing is, a program is really a mechanism, or you can think of it as a bridge between what the user wants the computer to do and then what the computer is doing. Now, what is today's talk? Well, so I wanted to kind of motivate the programming side by looking at some of the history of processor development. So we'll go through from the 70s up to now, how are the processors being developed and what are the features they have and how that actually impacted programming. And then we will talk a little bit about, going forward, in the next 20, 30 years, how a processor design going to look like and what are the implications for them on programming. Okay, so we'll start, right? So this is a computer performance roadmap from the 70s to about now, and then our projection going to 2020. You can see I kind of labeled them with some of our processor from Intel. And a couple of things I want to talk about in this picture here. One, you can see that the trend is always continuously increasing. So the Moore's law is still well and alive. So we continue to crank our processor with more and more transistor and continue to pack more and more performance onto it. The red lines kind of shows some of the supercomputers that the world has been building. And it's actually increasing almost 1 billion times in performance. Now, the other interesting things are the blue dots and the green dots. The blue dots represent processor that goes into our desktop processors. I know some of you may not even have a desktop these days, but those are the computers that we work with all the time. Now, the green ones are the handhelds, like the phones that John talks about, right? I'm sure most of you will have a smartphone today. And the interesting thing, as you can see, the trend is actually in parallel, meaning that the desktop processor are tracking the performance increase of supercomputer, just lagged by 1 or 2 decades. And same thing as the handheld processor, it's actually lagging behind the desktop processor by 1 decade or so. Now, the key thing to learn from here is that, well, we're going to have a lot of computing capability to our process, to our devices. Both your laptop or desktop computer as well as your phone and things that you carry around by year 2020. What do we do with them? Okay, so we're going to go back and look at some of the early semiconductor processors. So now we're going to fly back in time, back to the time of 1960s and 1980s. So this is really the beginning of semiconductor processor. Computers actually started a long time ago in the 1800s, but those are more mechanical processor. In the 1960s or so, silicon transistors are actually really being developed. And around 1970, a few companies like Texas Instruments, Intel, Morse Technology, Motorola, and so on, starting to put these together using what we call large-scale integration. And you can see that at that point, the number of transistors are relatively small, around 2,000-3,000 transistors, versus we're talking about billions of transistors or processors today. So these are really elementary, but they are really the beginning of the CPU or the processor that we know today. Now, again, since this is very, very early on, until late 1970s, when IBM introduced the first PC, that's actually start revolutionizing the whole PC and the computing industry. Before then, it's always in the department or in some government agency. Now, how are programming like in these early semiconductor processors? Now, by and large, first of all, these processors are not very capable. They can only do very few. I mean, they run in megahertz. I'm sure some of you may not even know. Think about comparing to today. It's about 1,000 times lower than the processor today. And then they have very limited memory. Talking about the early computer only have like 4 kilobytes of memory. Even the later one, the PCs only have 640 kilobytes. I mean, even our cell phones today have gigabytes of memory, so these are really ancient. Now, the types of program, so the operating system, like John was talking about back then, we have very, very primitive operating system like DOS, which is what makes Microsoft very famous, and Unix, which is more on the mainframe or the workstations. Now, because these are mostly command line based interface, so therefore the people really don't care about graphics. Even when they're talking about graphics, it's really you have all these characters that put together like a picture, rather than really nice JPEG pictures that we all look at today. And in terms of computing languages, in the 60s or so, some of the languages that we know today, like C, Fortran, it's already been developed. And they are actually mature by then. But by and large, at this point, mostly limited by the small memory footprint, people cannot really write large programs, right? Because your program is going to be sitting on a disk, and then you need to load them into your memory to use. And so, therefore, people really spend a lot of time compacting the functionality into as few instructions as possible. So programming at that day and age is actually quite difficult, and actually have very limited functionality. Now, getting into the 80s, from the 1980 to around 2000, we started having, the semiconductor manufacturing technology become more mature now. We can actually start packing more transistors, talking about hundreds of thousands of transistors to starting to be like 1 million transistors or so. And also, we rapidly increases the processor speed during this 20 years or so. And you can see I listed, there's almost like 10 different Intel processors being developed inside this 20-year time frame. So the cadence is increasing very rapidly. That the processor performance has increased significantly, and the capability of these processors become more capable, and so people can actually start doing a lot more things with them. And in terms of usage, it start rapidly expanding into, not only very large business can have computer, now even small business can start having computer. And in the home side, really the gaming market takes off. During this period of time, there are a lot of game consoles starting to show up, and many of us grow up in this age by playing computer games on these consoles. Now, in terms of programming, one thing starting to change. Windows, I think this is Windows 3.0 or something starting to show up in this time, and then of course, right, Apple have their Macintoshes, and graphical user interface starting to revolutionize how human beings interact with these computers. Prior to this age, it's all command-based. You sit there, you type in your command, and then that's it, right? I mean, the computer does something and returns some numbers to you. Not that much graphic stuff. Until this time, the GUI interface starting to shows up, and then the Windows interface starting to becoming the norm of how we actually interact with these computers. And of course, right, with Windows, you have mouses to point to where you click, point and click starting to shows up. And then the other thing is, during this time and age, right, as we adding more functionality to the program, make the program more human, make it more human so that you can actually interact with it easier, it actually put a large constraint on the processor performance and the amount of memory it will have. And this is really the good age in some sense that because there's a rapid increase in processor frequency. So in terms of computer architecture, this is kind of like a sort of one of the golden age in computer design where we're starting to have more and more transistors, so you have more freedom to put, to put more features into your processor. And the goal is to make performance, increase your performance. And because of that, and people really have a kind of instantiate appetite to get more performance from the processor because they want the computer to do more for them. Now, in this day and age, literally, the way to increase performance of these processors is by increasing the frequency. We actually increased the frequency about 100x, maybe a little bit more than 100x from 1980 to 2000. So processor running at around 10 megahertz, at the early 80s. And by the year 2000, we have the first gigahertz processor. So it's 100x increases in performance. Now, what does that translate to your program performance? Is that because people still write the same program, as the processor frequency increases, the program automatically get more performance with a newer processor. So it's kind of like having a free lunch, right? So I could still keep my old program, and I just need to buy a new processor. And also, this is really a good age for Intel, where every new processor come out, they sold out in a day or so, right? Because people just needed more performance. Now, what is that translated to your programmer effort? Because they don't need to focusing on increasing the performance of their application. They just need to buy a new processor. So they actually start switching the effort into creativity, and that's what I was saying. Now you're starting having new user interfaces, right? Like graphical user interfaces. AI actually starting to pick up at this point, but because for artificial intelligence and so on requires so much computation that most of the computer, it's way before its prime time. But people do think about, how can we actually be more interactive with the computer? Speech recognition, facial recognition, gesture recognition are all discussed in academia at that time, but they cannot be realized yet, just because the processors are not quite ready, and also because of this excitement about you got a processor keep increasing in performance, you got more and more usage of these processors, so everyone really start talking about computers. and everyone wants to do programming. Now, what happened, after year 2000? There is as we actually pack more transistor into the processor, as we keep cranking up the frequency, some phenomenon happened. The key problem here is that the power density increases rapidly. That's just, you can imagine that the more, for the same area, you're packing more transistor. Each transistor is like a switch, right? And the frequency, it's like how fast you switch it. Now you can imagine that, for the same area, you're doubling the number of switches in every 18 months, and you're increasing the switches rapidly. The speed up, you're turning on and off the switch rapidly. What it translated to from a physical term is that it actually dissipates a significant amount of power, and it actually increases. And because that dissipation of power is on a smaller and smaller area, so therefore the power density actually increased very rapidly. By year 2000 or so. I was talking about we having a gigahertz processor, but these processors already dissipate quite a bit of power, and also the power density inside these chips is enough to melt most of the conventional packaging, and so therefore we need to start put heat sinks and other things on top of these processors to dissipate the heat. The issue on that is that that kind of preventing us from processor designer to further increase the frequency. You can say, well, can you increase the frequency? Yes, we can. In fact, we have a lot of prototype in the labs that actually can increase the frequency of these processors up to several gigahertz, maybe even 10 gigahertz. But the problem there is that the power density of these processors increase so fast that we pretty much need liquid nitrogen cooling these processors to prevent them from melting or malfunctioning. So as you can see in the trend, right, from year 2000 to 2010, this 10 years, we have only increases the processor frequency by about 3x. Versus in 1990 to 2000, we increased the frequency by 25x. Was there a question online?
Yeah, Victor, because I actually asked questions in between for the other two speakers as well, so I just wanted to get your permission if I can ask questions. Just so you know, the audience, some of the audience is not that technical, so I know a lot of the guys here will grasp this. But at a high level, would you say, because this is an amazing development on processors that you're showing here, and I know a lot of these people, students here have heard about it. Would you say software engineers have pushed development of more powerful processors, or is it the internet? Or what are your thoughts on why this development has been happening so fast? Who are the key people that has driven this development?
Well, usage is always the driving force for processor development, right? I think in the early, in the earlier stage, right, from the 80s to 2000, it's essential. You can think of it back then. It's really word processing, spreadsheets are really the driving force. Because computer. Think of it back in the early. So again, I'm trying to introduce as a history, so I understand for those who are not, majoring, electrical engineering and so on. Just think of it as listen to the history, right? Early computers are developed mostly for military use, for scientific use. They do large-scale computation, okay? And so the average people on the street doesn't have access to them. And then later on, large business, starting to have departmental computers, and only those, and then these machines are very, very expensive, and only very large corporations has it. In the 80s, there are two things that actually start motivating, people wanting faster processor. One, certainly, it's the small business, because the introduction of PC makes it affordable for small business. Even then, it's not cheap. The first IBM PC, I think, is about $2,000-3,000 in the 1980s. It's very, very expensive. But then again, it's still affordable. So smaller business starting to make use of them, and then the primary usage model there is really word processing and spreadsheet. those are really for them to do accounting, the communications and so on. Now, the other front is actually the gaming industry. Now, of course, these processes are very different for gaming usage versus the business usage. So, but those, again, right, the software developer developed the software for it. But then again, whatever they want to do, the processor at least before year 2000 are too slow. And certainly, they just, so basically they wanted faster and faster processor, right? I mean, imagine if you're typing, let's say you have a typewriter, but every time you press a button, it takes a second before that character shows up on the screen. That's too slow for you, right? So you want it to be faster. Now, once you can type fast, once the computer is fast enough, as soon as you type, as the character appears, you also want it to be able to do calculation. In the past, when you run these spreadsheets, you really literally don't update your calculation every time you change your number. You have to press a separate button to say, okay, now update the calculation so that it will refresh. Otherwise, and then that refresh typically takes seconds. And so you can see, right, that user experience of being, things are too slow, and people always are eager to have faster and faster speed, kind of motivate faster processor. Now, I think around year 2000, that's when we actually switched to the point where these word processing, spreadsheet calculation, it's actually fast enough. Now, the things that drive the development from year 2000 partially is the internet. The explosion of internet, everyone just wants to be part of that and be able to, share the information, being able to, check out what's going on, really drive the growth of saying now we need more processors, right? Cheaper and faster processors. Well, not necessarily faster, but cheaper. Now, and then the other thing is, like I was saying here, is the technical challenge that it is more and more difficult to build faster processors. So how does the industry react? Is saying, okay, well, we won't build the processor too much faster so that we will have to pay for a very expensive cooling solution. But instead, we actually switch from, instead of one processor for one core per processor, to have 2 cores or 4 cores and multiple cores. And so therefore, we enter this age of what we call the multi-core processors. So, but does that answer your question, or does it help you set up a stage and understanding what's going on over this period of time, and why are the processor design changing, and also what motivates them?
I believe so. Yeah, it's very very interesting. We're eager to hear whether we're gonna have i60 chip.
Okay, sounds good. We'll move forward to the next stage.
Can't wait until you talk about the red dots up right corner.
Oh yeah, the red dot. Yeah, we will go there soon. So,
okay, great.
Just to kind of, I think I'm almost having like one or two more slides, then we'll start talking about future processors. Now, just to finish up, in the multi-core era, and especially like right around 2010 or so, as also I think Jordan mentioned that too, the devices that actually use this processor have grown exponentially, especially the popularization of our smartphones. Right? They really changes the game a lot. So people actually need to start, think about the program, how programming have changed, right? From the days that you can only sit there writing text-based program, and most of the goal is really to do sort of calculation. To when you start having Windows, you have some elementary graphical user interface, and being able to display things more intuitively and be more engaging, to the time that now almost everyone has some kind of smartphone, have some mobile device that can actually do computing and be able to connect with each other. And also, the rapid programming development is actually becoming important, right? In the past, like I said, when you're writing text-based program, it's relatively easy for you to debug. But as you add more and more components, especially the graphical component, the internet components to it, programs become complicated. And you really need, and also the cycle, right? People really want to be able to quickly develop a new program. So scripting languages and also more safer languages like Java and so on, so that the programmer doesn't have to deal with a lot of the nuance underneath the hood, right? How you allocating memory, how you manage the memory management, and whether you need to free it and so on. I mean, those are handled by more or less the runtime. So that makes the programming productivity increases, and that's actually a critical component going forward. Now, so we are talking about future processors now. So first of all, as I think that question you asked earlier is great. You know, what drives the development of processor? So to look at future processor, we need to understand, how these processors will be used. At least from our view, it has a few things, right? It's going to go to everywhere, beyond, just the traditional form factor like computers, laptops, or smartphones. It's actually going to be integrated with, your appliances, even, your car that you drive around, glasses, watches, even at your clothes that you wear with it. So that, these processors will be everywhere. And you will have and then again, right, remember that computing roadmap I showed earlier, the performance of these processors will continue to increase. So that means that you're carrying more and more computing power around with you. And then the question is, well, how do you harness all of these computations? Now, future usages. From a personal point of view, it's certainly going to become things that we envision will be like smart personal assistants that can actually help you organize your schedule, that actually fetch news for you, that plan trips for you, and also warn you of dangers in your environment. So basically, the computer is no longer just becoming, you walk up to it and you tell it to do something and do it for you. These computers are smart enough that actually learns about your personal behavior, learns about your interest, and actually proactively does a lot of it for you. So that's what I mean by a smart personal assistant. From a business point of view, it's definitely becoming more in terms of business analytics rather than, yeah, my computers are used for my accountants to make sure my books are correct. No, it's no longer simple like that. It's actually much more proactive that it ran these large-scale analytical software that analyze a lot of data that you collect about your customer, about your supply chain, and so on, so that it actually both improves the business top and bottom line. And again, for governments, certainly large-scale systems are built for, intelligence services, trying to understand what's going on, preventing terrorism, preventing the natural disaster to happen, or in case when they happen, how do you coordinate, the agency and make it more efficient to solve them? Now, having these usage in mind, how would we build processor to actually solve, to make these usages possible? Okay, so I'm briefly going through, just summarizing the technology that we have used, right? So in the 70s, we have increasing mostly single processor architecture, single core processor architecture using pipelining, branch prediction, caches, and so on. Then in the year from the 90s to 2000s, we basically make the single core processor a little bit more parallel by introducing what we call SIMD processing, which is like a small vector processing. And then also breakthrough into computer architecture, going to what we call out-of-order superscalar processor, and then introducing caches to shorten the memory latency. In the 2000s and 2010, this 10 years, essentially we introduced multi-core. So having more than a single core. A core, you can think of it as like an engine in the processor. Most of our car have a single engine, but in our processor, we actually have multiple engines so that they can actually do more work. Going beyond 2010, certainly the trend is, we're going to have many cores. When we talk about many, we're really talking about literally tens of these compute engines inside your processor. Now, what else can we do with it? Well, so to understand what else we can pack into these future processors, let's look at how what are some of these technology and how they will scale going forward in the next 10, 20 years or so. Now, up to now, semiconductor, silicon semiconductor has been the medium that we use to design these processors. And the key things that we talked about there is these transistor size, essentially what we call the feature size. And essentially, the Moore's law said we can actually continue to improve the manufacturing capability to make devices that are smaller and smaller. So the numbers that are shown on the top left graph for transistor density is essentially the feature size. 45 nanometer. So today's processor is actually, well, today's Intel processor manufactured in the 22 nanometer, which is the 22 numbers here. And many of the other manufacturers are manufacturing around 30 nanometers. So globally we are around in this time and age around 20 or 30 nanometer. And we expect that each 2 years or so, you will actually move to the next generation of the process. So you can see from 22 nanometer to 5 nanometer, we have around 10 years time frame. And 5 nanometer is really, 10 nanometer is really, really small, almost down to a single atom now. Now, going beyond then, we will have to have new manufacturing capabilities. So the key thing about this is as we improve the manufacturing technology, we expect that we can continue to pack more transistor into your die, because that's what the transistor density do. But as we said, right, the power density is limiting how fast we can actually increase frequency. We can definitely see that, from 22 nanometer to 5 nanometer, we're not going to be able to increase frequency more than 20%. The other problem of semiconductor processor is the supply voltage, because there's a minimum gap voltage inside these transistors. You can see 0.8 volt is about the minimum you can go. It's very, very difficult to go below there. Yes, there are research going on to look at what we call subthreshold voltage that basically drop it to around 0.6. But certainly, it's very difficult to go down to 0. Okay, and so what the implication of what these three figures is, the last figure on the lower right, that basically is saying that normally when we actually improve the semiconductor manufacturing capability, go to smaller transistor, we should be able to have we should be able to consume less energy. But because frequency remaining flat and the voltage remaining relatively flat, the energy scaling, there will still be some decreases in energy, but not as much. Why am I keep talking about that? It's because, as I said, right, to be able to power these processors and be able to limit the amount of heat that it generates, it's very critical for designing the future processor. Imagine, right, we're going to put a processor into your clothes. Well, certainly you cannot carry a big battery with you. So therefore, we want to be able to power these processors by either just your body movement, or maybe a very tiny battery, or maybe even like a solar cell, right? But these things, because they're so small, they cannot generate that much energy. So therefore, the processor energy has to go into being capped by a very small amount. Now, there are a few challenges, right? Given this is the technology setting, unless some brilliant people out there somewhere is going to invent new kinds of manufacturing capability. If we're looking at the trend, as we said before, for the next 10 years, so these will be the challenges for us to build, bigger and faster processor. Number one, performance, right? Certainly, we cannot increase frequency anymore. So the only way to make use of more transistor is to actually put more of these transistor processor core into the same design. But then again, right, if we put more of these core in the same design, the design complexity goes up. And also, they may not necessarily directly translate to performance. We'll talk about the programming implication in a minute, right, of all of these changes to the processor. Second thing that I mentioned earlier, energy. So the key thing, again, is that, can we do more things? Meaning that can we keep increasing the performance but using less energy? And then the last thing is reliability. I think many of you haven't really thought about this particular point, because up to now, we think that our computers should just work, right? From time to time, if you're using a Windows computer, it will crash. Well, actually, these days the computers don't crash as much. In the 90s, it always have this blue screen of death that shows up once in a while. Basically, it just said, "Sorry, your computer just crashed. You have to reboot." Now, one aspect is that as we make these transistors smaller, they are actually more prone to failure. And also, you integrate a large number of these transistors together on the same die for a processor, that the chances of failing just increases rapidly. Now, what to do with reliability? It's an important factor. So to summarize, these are certainly, in terms of future processor architecture, features that we definitely look at. For example, a tile-based architecture, which will address both performance as well as reliability. So you can imagine a processor. So each of these dots here, you can imagine represented in a tile. And a tile may consist of a processor, some caches, and some interconnect, and so on. So if one of these tiles fail, so you can just say, okay, too bad, I'm marking off, and then now I still have many others to go with. But again, you can think about the implication to your software, right? If you're running something on that tile and that tile fails, what does it mean, right? So your program now needs to be able to recognizing that, oh, yeah, I may not be able to complete my entire run. So from time to time, I might have to checkpoint. I might have to move from one processor to another one in case the one that I was working on failed. Heterogeneous core and accelerators. I'm sure some of you might have heard of the term accelerator. So accelerator here means that you have a device that actually speeds up the computation. And for example, GPU is a good accelerator, but there's certainly way more accelerator out there that people are considering today. Heterogeneous cores means that instead of only have one type of core inside this processor, you can have different types of cores. And then again, the implication for programming is that now if you write a program, you will have one performance when you're running on one type of core, but if you switch to a different type of core, the performance might change. Now, what is this implication, right? Should I write different programs for different types of core, and so on? And of course, your memory hierarchy, well, the gap between the processor performance and memory performance continues to grow. There's something this is called memory wall. And the only way to bridge that gap is to have more intermediate levels of what we call cache or memory. And then the implication for your programming is that now, previously, you only thought, okay, I only need to write my program, and then that program will see all the memory in my computer system. Here, if you have different levels of memory, some are faster than others. Now you need to make a decision saying, okay, what goes into the faster memory and what goes into the slower memory, and what is the implication for performance. And redundant computation is essentially saying, well, my computer might fail. So one way to deal with these failure is maybe I start two threads doing the same computation. In case one fails, I still have one going. And non-volatile memory literally say that even though you power off your computer, the data will continue to stay around inside each memory. So next time around, when you power it back on, you don't need to go through that boot process and resetting up everything. The data still. Yes.
If you don't mind, just quick one. The guys here, they have inquired about, manufacturing plays a big role on processor development. Is that correct? Yeah. So, would you say that Intel is the company that has contributed the most in developing processor power around the world, or is there any other company that competes or to the level of Intel when it comes to manufacturing?
I would say actually, from a manufacturing point of view, Intel is sort of the world leader in developing, new semiconductor process technology. Now, there are certainly many other companies in the world, IBM, TSMC in Taiwan, Samsung in Korea, and some of the Japanese manufacturers, right? We all work on, and again, it's not just one company, but we certainly spend a large amount of money in terms of research and trying to figure out what to do with the next generation process technology. But it is a big ecosystem, and there are few. But again, there are not too many players now. I think the number of players is down to around less than 10 now, because just the fact that it costs us a lot. For us, it costs us billions of dollars to build one of these fabs. And so not too many companies in the world can actually afford to actually build these kind of factories.
Okay, so just to emphasize, you have to have manufacturing experience to build the processes for the next trend. There cannot be a company out of Kosovo that says, I want to build processors, and they have zero manufacturing experience. That's the way it goes, right?
Well, but then I think the web, I mean, okay, so in terms of processor design industry, now, there are two ways to look at it. What I mentioned earlier is about pushing the processing technology to the next stage, right? So those are more research oriented. In terms of, if you're a startup, you want to start building a processor, these days, I think majority of the companies out there actually uses what they call a fabless model, meaning that they don't have their manufacturer, they contract it out. So companies like TSMC, this is a company in Taiwan, Global Foundry, IBM. IBM nowadays mostly have a very small capability now. Samsung. So they are the manufacturing powerhouse that people who want to, like for example Apple, they don't have their own manufacturing side. They have their own processor that goes into the iPhone. So what they do is they have a design team that actually designs the processor, and then they uses these manufacturer, one of those, to actually manufacture their processor, and then they put it inside their phones or their tablets, right? And so the model, what we call a fabless manufacturer, a fabless design house, has actually become very, very popular. Now, the other thing is what we call ASIC or FPGAs. So those are FPGAs is essentially chips that are reconfigurable and programmable. So a lot of these small startup actually uses them for prototyping their design. So startups in Kosovo or anywhere in the world where they don't have the manufacturing capability, they can certainly use these models for them to develop their processor.
I see. Okay, nice. So just to put flavor into this because of the audience, how would you stress out a processor? Let's say you are doing research for a powerful processor. You have maybe you have it on the other slide, but is there a process to stress out a processor? Do you like attach a lot of computers to one processor, so you push a lot of computing power to that? Or is there something that you guys test as a processor when it's ready?
Well, certainly, right? I mean, there are many ways of testing or stressing a processor, but in general, I think your idea is right that we run a larger number of programs on the processor and trying to see how well they work. Now, we usually do it. There are two ways of doing it. One is we actually design specific benchmark that we know will stress the processor and just runs it. The other way to look at it is, well, again, right, application driven, meaning that let's say we work with some customer in the world, right? So they said, oh, I have this program that I want to run on your processor. So we take that application and run it on the processor and do analysis and trying to understand, what part of inside, you can imagine, right, with a processor is made up of many, many components. And when you ran an application, not necessarily all the components are being stressed, maybe only one of them, maybe a few of them. Now, the goal is to understand which are these ones that are being stressed. And then the question is, they are stressing the processor, is it because of the way the program is written, or is it because of the way the processor is designed? Those are very different. If it's because of the way the program is written, there are many ways to solve the problem, right? You can suggest to your customers, say, okay, well, we looked at your program, and here are some things that you can improve, and you can get more performance out of our current processor. If it's something related to hardware, then literally you need to go and figure out how you can redesign your processor. Now, I want to emphasize is the cycle, right? The amount of time that you need to take to fix that problem is much, much different. Fixing a software problem could be a matter of months. versus fixing the problem inside, or fixing a performance issue inside a processor could be years. So the scales are very different, and of course the impacts are very different.
So very interesting. I know a lot of these guys know what a for loop is and a while loop. So if we break a for loop, does that stress the processor? Like let's say on I equals 0, I less than, and you just put a weird character in there, the for loop does not actually break. Uh, does that like return that the processor is overloaded and you see what I'm saying?
Well,
Like
it depends, right? So okay, so I think you're hinting into a parallelism. Maybe let me go a little bit forward. So
yeah, sorry about that.
well, I was gonna there should be a slide that talks about parallelism, but anyway, so let's back here for a moment about parallelism. So as I said, right, one of the key things is going forward, the processor is going to have many of these so-called compute engine or cores. Now, for you to really harness all the compute capability of the processor, you need to make sure every core is doing something. So let me make an analogy. Right? You go to a bank, and a bank has multiple tellers there. Right? Each teller, you can think of it as a core that does some work. Right? Now, so let's say you have a bank with 4 tellers. So if you only have one customer comes in and talk to one of them, the other 3 is doing nothing, right? So certainly you won't call that a stressful environment, right? So same thing in a processor. When you only have one of the units or one of the core doing work, the others are not doing work, then that's not stressful. How would you stress it? Well, bring more customer in, right? So imagine now you go to a bank, on a Friday afternoon before a long weekend. Everybody wants to get some money, right? So you got tens of customers left standing in line, and again, you still have only 4 tellers. Now, these 4 tellers will be very busy, right? Because as soon as they're done with one, another customer will walk up to them, right? So this is what we call parallelism. Now, many applications does have inherent parallelism. So it's important to explore the amount of parallelism that your application would have to stress out a processor. Now, back to your example of a for loop. Now, when you write a for loop, you still need to analyze that for loop to understand, whether each iteration of the loop are they really truly independent? If they are, that means that your for loop have a lot of parallelism. So that means that, yeah, you have many of these customers, and then they can be served independently. Versus if you have dependency, basically it means that I need to serve customer 1 first before I can serve customer 2, and they are related. Therefore, so imagine, right, there's 10 customers standing in line, but they all related to each other. And then also, you must serve the first customer before you can serve the next one. So that is what we call serialization, or you have data dependency. And in that situation, yeah, even though you have 10 customers, but you have 4 tellers, but only one of them can do work at any one time. So does it make sense?
Yeah, I was on mute. Yes, it does. Thank you.
Okay. Yeah, so essentially that's how we stress out the processor. Of course, right, when these processors have tens or maybe 100 core, you need a large amount of parallelism for you to actually, stress out the processor. But anyway, I think in the interest of time, let me move through my next few slides quickly, because I think that would be interesting to some of you that talked about, what are programming challenges for future processors. Okay.
Okay.
As I said, if you look at this figure here, up to year 2000 or so, most of the programs that are written at that time is what we call single-threaded application. And literally, as we increase the processor frequency or processor performance, these programs will just get better performance. They really don't need to do anything. But as you actually get, beyond year 2000, actually around 2005 or so, when the first multi-core processor shows up from the commercial space, you really need to start be aware of what we call the parallel resources. There are actually lots of parallel resources in our processor today. I mean, even your cell phone, you have multiple cores in there. You have vector units, this so-called SIMD unit. So some of you heard of the term SSE, MIMD, SIMDs, and so on. These are all related to saying that inside each of the processor core, you can actually do multiple data computations simultaneously, as long as they have the same type of operation. Now, again, these are what we call the parallel resources. And then the other thing is, you need to be aware of the underlying architectural limitation, like how the memory are being shared. Now that imagine previously there's only one core and he only sees one cache and one memory. You have all of them to himself. But now, if you have multiple core in the system, they're all sharing the same cache and same memory. Now, data contention becoming critical. You don't want one core comes in and said, I need this data, another core comes in and then actually took the data away from him. So these are some of the limitations that you need to be aware of so that you can actually get back onto this tuned version or the better performance. Now, in terms of challenges, there are two things. On one hand, everybody, well, up to now, most of the programmer thinks sequentially. When you think about writing a program, you will say, okay, I start doing this, then I do this, then I do this, then I do this, right? So it's a very sequential thinking. So in terms of programming effort, there are some programming effort, but it's certainly smaller. And then you only get a certain amount of performance. When we talk about the tuned performance, you really talk about, okay, well, how do I make use of the available parallelism inside my program? How can I actually make use of the parallel resource in my hardware, and how you map them? And that gap is very large. So the two key aspects here is programming effort versus performance. And we always know that if you put more effort in, you will get more performance. So from a programming environment challenge point of view is that, can we get to this red star here so that we increases the programming performance effort by a little bit, but we get a lot more performance. And that's kind of where we want to get to. And then here's an example of some of the future how we do programming in the future is what we call problem-solving environment, right? So example is MATLAB. I hope some of you know what this is. It's kind of like a mathematical program that actually allows you to do solving a lot of math functions very quickly. And it's used by a lot of scientists. Now, so the key here is that the programmer comes up with a high-level idea of what you want to do to solve the problem. So you want a prototyping environment. So this is what we call a problem-solving environment. And MATLAB is just an example. There are many other out there. And essentially, you want to quickly write it up. Now, of course, when you do that, initially the performance is not going to be great. Now, today, this green boxes to the right, it's all manual, right? We hire a lot of these, what we call ninja programmer, who really could understand, the algorithms, the code, and the underlying platform, so that they actually optimizes it. But what we really want to have from a research point of view is, can we actually have a software system that automatically does this? So that's what we call a smart framework. That number one, that generates optimal code. Number two, it performs a lot of these very low-level optimization for you. And number three, it parallelizes the code so that it actually can run on all your parallel resources. And lastly, because you could have heterogeneous type of resources, so they have different performance, so you need a scheduler to schedule them to understand the right amount of work, so that they will actually get the best performance, and that gets you the optimal program. Now, again, so this is sort of what we're working on in terms of a programming environment going forward. And I kind of want to end by saying that, for as long as there's computers are always motivated by what people want to do with it. And we actually see that, there's lots and lots of opportunity out there. And today, from developing better sciences, have a better way of understanding our financial market, having help develop medicines that actually can save lives, doing more energy researches, and how do you deal with disaster situation during simulation and so on. So I mean, there are really a lot of opportunity out there. So my last statement to say is, I encourage all of you to think big. Even though you're not a programmer, think big. What can these computing capabilities can do for human beings, and also learn how to program so that you can make use of these resources and realize your dream. So that's the end of my talk. So I'm open for questions if you guys have some time.
That's great, Victor. Thank you so much. I was actually talking parallel and explaining some of the stuff here into a different language for the guys here.
Sure.
And, it's very interesting. Of course, all the three topics are so intuitive that will fall in our domain as we learn here at in different languages and different applications that we build at Washington Education in Kosovo and in Albania. And let me see if there's questions around the table from the two centers, and then we'll ask people here if these guys have any questions. But you wanna let me pass it to this time. I guess Protek in Albania. Where? Isak?
Yes, Ridvan. Unfortunately, we don't have the questions at this point, though we have to admit that at the very beginning we had a couple of technical issues in connecting with you guys with one of our computers, and nonetheless we had also some connectivity issues, you know, with with quality of the voice and stuff like this. Anyhow, that's not the excuse that we're trying to come up, but we wanted just to thank Victor and thank you all for giving us the pleasure to be part of this intriguing and very interesting conversations that we have been able to share with you guys. Thanks a lot from Tirana, and I hope that we'll be able to meet up again. And my compliments to all the gurus, you know, that they have helped us, you know, get all this knowledge that we hope that we'll have them again. Thank you very much.
Just so you know, this is all recorded, so everybody can watch the recorded version. If there's been any technical issues, you can just, I guess, go and play from the beginning. Okay, so the center from Protek, thank you, Isak, again for hosting this. And please feel free to pass this to others that were not present. I'll go ahead and pass the microphone to ICK, Innovation Center of Kosovo. Do you guys have any questions?
Yeah, I have a question about the process. And will it be possible? Hi, do you hear me?
Yes.
Okay. Will it be possible the processing to be by talking, not by typing the buttons? For example, when you want to create or build a program or website just by speech, not typing anything.
Well, certainly the human interface, right? So as I mentioned before, even in the 80s, people already start thinking about, you know, different input mechanisms, different ways of interacting with the computer. Speech recognition certainly is one of them. In fact, I mean, object-oriented programming is actually also there. So rather than typing code, you have code that are actually already predefined and into like an icon or something, and you can actually drag and drop and actually connect them together. There are many things to do. Now, in fact, I mean, a lot of these artificial intelligence, machine learning type of algorithms, they want to go beyond, you know, just the programmer telling the computer what to do. They actually want the computer to learn themselves, right? So, for example, the latest, for example, recognition type algorithm, it's actually done what we call neural network. In a neural network, you don't predefine what you're trying to look for, but actually let the system run, and by going through many of the pictures or samples, it will actually figure out, you know, what is the things that it is looking at. So it's actually quite intuitive, very interesting, intriguing, and going forward, I would say, I don't know, maybe 10, 20 years from now, computer will actually starting to be able to think on itself. So meaning that you can come walk up to the computer and say, oh, computer, I want you to, and it will actually go and figure out and write its own program and actually go look for that thing and then bring it back to you. But, you know, this is more science fiction.
We have seen movies like
I think you guys are on mute, so I cannot hear the question if there was a comment.
Yeah, no, I said that we actually have seen movies like that.
Yes.
Where you
So
talk to the
today is the
computer.
movie, but I can tell you certainly a lot of researchers around the world is working on that.
Okay. Any other questions from ICK? If you have questions, you'll have to unmute yourself. I already accepted.
No, thanks Ridwan and Mr. Lee for the lecture. Thank you for everything. We don't have any questions.
Okay, we have a couple of questions here on our end, and then I guess we can wrap up this last session. One question from Artan Ahbeti: when people will have a quantum processor inside the PC, a quantum processor?
Well, quantum computing is something, I think it's been around for about a few years. In fact, a few years ago, University of British Columbia has a quantum computer they designed. But those are very large-scale prototyping machine. And putting it into a processor today is still going to be a long way to go. So I don't know exactly when, but it is certainly an area that a lot of people are interested in and working on.
Okay, Trim Bresa says, what price will these supercomputers have? Please don't put them on Apple because they're so expensive.
Well, supercomputer these days are on order of millions to billions of dollars. So only country can buy them. So typically each country might have one. But it's interesting to see, more and more countries around the world is buying and building their supercomputing center.
So, Victor, as programmers, are we going to have easier life by having more powerful processors? And we put different layers of programming languages. So at our end, when we build an application, we can just write one line of code and it will do the job for us.
Well, that's the hope, right? So that's why I was saying at the end, towards the end of my talk, these future problem-solving environment hopefully is powerful enough that you can write more intuitive code. It's more like, it's not really one line, fewer line of code, but more like something that closer to what you're thinking of. So if you're trying to solve a problem, if I can express the program in the way that the problem formulates, and I don't have to worry about the syntax of the program, I don't have to worry about, how do I make use of all the cores. That's where the power comes in, and these systems are being developed these days. But I think it will take a few years before it will be on the market.
You hear that, Isak? Isak is the executive director of WEA. He's not technical, he doesn't code, but it looks like you're going to be able to code.
Yes, so then everyone can code. That's the good thing.
Yeah, I guess you're right. Maybe in a couple of months.
All right. All right. Well, thank you so much.
Well, I think it's more on order of years than months.
As a matter of fact, while listening, to all the conversations, I mean, it's like at the very beginning, I thought that it's going to be a rocket science for me. By the end of it, at least I'm encouraged, to start looking at it.
That's good. That's good.
We break the ice. Good job. All right, Victor, thank you so much again. I'll just point to the audience here as much as I can with my computer not messing up.
Thank you, everyone.
And thank you so much for the presenters, the ICK and the ProTech, and really appreciate your time. Victor, enjoy your rest of the day in San Francisco. Here is nighttime, 9:18 p.m., so we're going to call it a day.
I see. Good night, guys. Thanks for joining.
All right.
Bye.
Bye-bye, everyone. Thank you for joining.